Unfortunately, we can't go that far. In biochemistry, yes. But not necessarily. So why might we say it's exothermic? We could run, but it's biochem. What do you got? Okay, it releases energy. How do you know it releases energy? Yes. ATP is our power horse. It's what supplies the energy. So in the conversion of ATP down to ADP, we have to release energy because ATP is our energy storage. So using some of our knowledge already, we can start to imply certain aspects behind it. Okay? What else could we look at? Okay, catabolic. You're cheating and looking at the slides, aren't you?
Well, not technically, because I had two choices and I figured out which one it was.
So catabolic is a biochem term, okay, or a biology term, bringing in, and because exothermic is too difficult of a term to use and continue to use consistently, so we invent a new term to make it sound cooler, because now we aren't copying chemistry, we've got our own field. Okay, so we've got catabolic. Okay, and catabolic is referring to, as you were talking about before, breaking down. Okay? How do we know we're breaking it down? We started with 2 things and we ended with 3 things. We broke something down. Okay? The one I'm kind of fishing for really only goes to those students that took 152. And I know you're going to be like, I don't remember anything from 152. That's okay. See what you can remember. So if you took 152, think about this equation. What else could we bring in? Okay, heat. Okay, that could help us with this. We'll avoid the catalyst term for the moment because we don't have that. Heat, typically measured in chemistry as our energy or enthalpy. Okay, we have the bond energy. By breaking that phosphate off, we have released energy into the system. That's why it's exothermic and catabolic. So we have an enthalpy that we could look at. Does that trigger anything? Flashbacks of horrible memories? Enthalpy and entropy. Okay. The enthalpy ends up being a negative term because, again, we're releasing that energy. What about our entropy? Okay. Why is the entropy positive? Why are we increasing disorder? 2 to 3 things. So more objects means more motion. Okay? And entropy is really, despite what people define it as a measure of motion. If I have more objects, there's more possible motion. Entropy must increase. Okay? Which then drives into the next possible thing. Is entropy a form of energy? Yeah, it is. Enthalpy? Is that a form of energy? Yeah. So interesting. We have 2 energy terms that we're defining, but they both contribute to energy. So what could we define as our energy for this reaction? As a hint, someone famous took these 2 terms and said, hey, they're both energy terms, let's combine them into a single energy term that we can use to represent an individual reaction. Our Gibbs free energy. Okay? And our Gibbs free energy, and I know everybody's super happy to hear about this, our Gibbs free energy is typically represented as a G. Our entropy is represented as S. Enthalpy is represented as H, kind of for heat. Okay. Just as a random side note, anybody get confused between enthalpy and entropy every so often? Yeah? You at least said yes, so I appreciate that. Okay. Anybody know why the term entropy was created? Because really, it's a word, we invented it. Why was it called entropy? Okay, allegedly, I think you trust Wikipedia. The guy that discovered it thought it was important enough that he wanted to make sure nobody forgot it. So he picked a word that was similar to the one that everybody already knew, enthalpy. Literally invented a word to be confused with another word contributing to energy. Awesome. Okay. We do get a different symbol, thankfully. It's not a lowercase h. Okay. Okay. But those two terms contribute to our overall energy. Well, how do they contribute? Okay. And this is an interesting dilemma because the entropy in this case is positive, but the enthalpy is negative. Okay. So should I add those two terms? Should I subtract those two terms? Are they both exactly energy? Anybody remember? Gibbs free energy, G, is defined as
delta H minus delta S multiplied by temperature.
HTS. We're typically looking at deltas. Why do we look at deltas? Because it's very hard to measure the entropy of one thing. We can measure the change pretty easily. It's not so easy to get the exact value for that exact thing. Okay? So we can look at our changes, so you're typically responsible for looking at that. For those of you looking at the MCAT, I think they ask questions along those lines. Yeah? Okay? Which is kind of irritating, and that'll pop up here in a second. Okay? So we've got a lot of information just buried in just a straight up equation, and using your general knowledge of what you already knew, in theory remembered from past classes, and kind of stacked that into this. Okay? And that's a lot of what we're going to do in biochemistry. We look at something and then throw in everything we've learned from the past and start defining things out. Okay? So, did I forget anything? Irritatingly, in my opinion, we get exergonic and endergonic. Why did we need a third term to represent the same thing? Somebody powerful enough decided that that sounded cool enough that we're going to include those extra terms. Okay? Catabolic was referencing breaking things down. Okay, so our breaking down is tied to our exothermic, okay, in biochem, because the catabolism and anabolism are biochem terms, or biology terms. Okay? So, when we're looking at catabolism for biochem, energy out, we're looking at a negative value, which is always nice and intuitive. That negative versus positive is an arbitrary system. We decided that it made sense for energy leaving to be negative. Okay? Did it have to be? Not necessarily. We could just as easily switch the sign. And we do in some cases. Okay? Again, referencing 152, cell potentials. Cell potentials, a good cell potential is positive, not negative. So we end up flipping our interpretation of those signs. Okay? All of that then folds into what I would say is 152. Okay? That picture at the bottom is your 152 class. You did a bunch of calculations, right? Okay? You looked at the speed of reactions. Well, what was the speed of the reaction dependent on? The activation energy. Why do we have an activation energy? Well, it's the reactant transitioning to becoming the product. Okay? We can correlate that energy difference to the time it takes for a reaction to occur. Okay? You might say, well, okay, well, what happens if I drop the product energy lower? Well, if I drop that lower but don't touch the transition state, what happens to the speed of the reaction? Nothing changes. The only thing that affects the speed is the relationship between the transition state and the reactant. I can do anything I want to the product. I can make it higher, I can make it lower. Transition state will always be the same. Well, as long as we pin it. The rate of that reaction will never change. Okay, which is kind of a weird statement to make, but it ends up being relatively true. Okay? Which is why when we look at 152, you really split it into two sections. Kinetics, and then thermodynamics. Because if I have a lower energy product, would I expect that reaction to be relatively easy? Is it easy for me to walk from the reactant to the product if the product is downhill? Okay, yeah, all I gotta do is trip and fall and I roll down to the bottom of the hill. Okay? That reaction we would then start to think of as easy to occur, okay, and I'm intentionally avoiding that word, okay? The science word that we bring in is then spontaneous. What's the issue with spontaneous? How many of you are spontaneously combusting right now? Anybody? Every single one of you is. Okay? It is not a natural state to be a human form. What are we constantly doing? As you are sitting here and breathing, what are you exhaling? Carbon dioxide. Where did that carbon dioxide come from? Your cells combusting to form CO2 and water. You are spontaneously combusting. What is the issue with the term spontaneous? Most people translate spontaneous to mean instantaneous. No, not in chemistry. Spontaneous just means it can happen. Okay? It is naturally designed to happen on its own. That is referring to the thermodynamic aspect. It says nothing about how fast it happens. Okay? Just kind of a neat little nuance of it and annoying because of English. Okay? So it's not chemistry's fault, it's English's fault. Push the blame. Okay? So where do we put all these extra terms that we've talked about? Well, we've got reactants, we've got products, we've got a transition state. Okay? We talked about an activation energy. What would that activation energy correspond to? Okay, the point is getting from reactant to product. How much energy do I have to put into this system to get from the reactant to the product? I have to clear this barrier. That is now my activation energy. Or E for energy, sub A for activation. Okay? What about the other terms we just talked about? Our Gibbs free energy. Okay? Gibbs free energy looks at the sum of all energies. Well, what are we looking at when we're looking at this energy term here? That energy is actually referencing everything. That energy is better written as the Gibbs energy. And when we're looking at the energy for an individual reaction, we actually don't care about the transition state. All we're comparing is our reactants to products. I don't care how I get there, I just care about the ultimate change. Which means, where do I find the Gibbs free energy on this curve for the reaction? It's the difference, conveniently labeled as G there. Okay. Where's the enthalpy and entropy? Much harder question. It's technically not there. It is folded into our delta G. Okay. And this is something that, as a very mild physical chemist, I get irritated at, because when you look at most textbooks references of the thermodynamic barrier, or the difference between reactants and products, they don't reference that as delta G. What do they call that? It's almost always written as delta H. But it's not the delta H. It has to take into consideration the entropy. Why can they get away with saying delta H instead of delta G? What's that? No, because that delta H is this delta H. There is no difference between them. Why is this term, T delta S, disappearing from this?
Temperature state constant.
So temperature is constant, okay, but if delta H is 1 and delta S is 1, that's a pretty significant difference. What's the big assumption that we're making to say we can call it all delta H? Temperature can't be 0, particularly for a biological system. That would kind of suck. Delta S is tiny. Okay? If we go through and typically look at units, the units for delta H, kilojoules, so thousands of energy units. The unit for entropy, joules. Okay? They are typically 1,000 units smaller than our enthalpy term. But if the temperature is 1,000 degrees, that scales it up and gets it important enough, right? So we could include it. Wait, what was this class? Biochemistry. In biochemistry, if we hit 1,000 degrees, there's probably no bio part of it, which means that term effectively disappears. And that's why we can end up calling it delta H. Kind of make sense? Okay. So I find this energy diagram incredibly important. If you've gone through organic chemistry or even general chemistry, this kind of thing should have shown up. Okay? And it should have gone into gory detail behind everything behind it. Okay? It is important enough that I will ask questions on the test, okay, based off of this. So if you open up the very first practice test, you will find an energy diagram and it says label the crap out of it. Here's all the things you need to draw on it. Okay? So you need to be able to identify those pieces. The units and the numerics aren't super important. It's knowing where to find that information. Everybody good with that? Okay. And I always throw this in mainly for, sorry, there's a delta issue down below. For kind of the med school end or even kind of any really pre-health test, they usually ask something about delta G. And they usually say, well, if delta H is this and delta T is this, is the reaction spontaneous or not, or some nonsense thing like that. Okay? That all comes from interpreting our equation delta G equals delta H minus T delta S. Okay? Understanding spontaneity comes from what happens with our sign. For a reaction to be spontaneous, what had to happen? The products needed to be lower in energy than the reactants. So when I take a delta, a change, I'm going to take the energy of the products minus the energy of the reactants. So for an easy spontaneous reaction, my delta G will always be negative. Right? So it's then going through and looking at what are delta H and delta S and officially temperature and saying how do all those things add or subtract with each other, interact with each other to make our reaction spontaneous or non-spontaneous. Okay? And so I've seen this type of table show up in a variety of study tools. I personally find it annoying, okay, and not worth memorizing because when you look at the question, you just have to remember a couple things. Delta G can be negative or positive. Delta H can be negative or positive. Delta S can be, T can be positive only, okay? Temperature must be in kelvins. Okay, so it can only be positive. So they may give you a ton of numbers, but it's really the sign on those numbers that's relevant. Okay, so let's clear up some space here. So if we looked at our ATP reaction, our delta H came out to be negative. Okay, that's based off of our pre-existing knowledge. ATP is our energy storer. When it breaks down, it releases that energy. Delta S was positive. What happens when we take those terms and bring them into delta G? We already know it to be negative, but let's see if there's conditions on that. Maybe we have to be at room temperature. So our delta H is negative, minus T. T is what sign? And our delta S was? I get minus a positive value. What is the sign on delta G always going to be? Negative. So one of the reasons why ATP is a great user for our energy, or a molecule for this, everything about its transition releases energy. There is no temperature dependence here. Okay? All the other terms, our positive, negatives, are just the all possible permutations and just plugging it in and saying what sign comes out of it. That, to me, is deriving it. That, to me, is memorizing it. Okay? And this is, I will continue to say, my biggest issue within biology. I hate memorization. I will always derive. Okay? So I'll end up showing you both. It's up to you to decide what you want to do with it. Kind of make sense? Okay. So, that was the end of chapter 1. We will come back to energy at the end of this, or not the end, but I think the third unit. So moving into chapter 2, water is cool. Water is awesome. There are huge reasons for potentially why we need to have water to have life. okay, particularly as we know it, but that's not really a fair statement to make because we have water. So of course it's important as we know it. Okay? Why is water important? Well, to understand that, what should we be looking at? Any ideas? Just write water. I just look at the word water and I go, whoa, awesome. Give it colors. Bonding characteristics, what do you mean? I don't see any bonds there. What it's made of. So water is actually H2O. That's better. Okay, what else do we need to look at?
Structure.
The structure. So we could draw out a Lewis structure. It'll be somewhat irritating. Is this a valid Lewis structure? Not really. Okay. Is it one that we typically accept? Yeah, why? We tend to imply lone pair electrons, okay, to satisfy octets. There's a lot of these implications that we just ignore. Okay. We could draw that on there. Is this a valid Lewis structure? It is a valid Lewis structure, and this brings in the next issue. Okay, this says large partial charge. To get a large partial charge, what has to happen? What is a partial charge?
It's a high electronegativity atom.
Okay, if I have a very high electronegativity atom, which is the most electronegative atom on the planet? Fluorine. Okay? And I bond that to fluorine. Do I have a large partial charge? No. If I am the only person on the planet, am I the strongest person or the weakest person? I'm both. To get a large partial charge, partial is a difference. I have to connect it to something else. If I connect it to the exact same thing, there's a copy of me. Am I the strongest or the weakest person now? Exactly me, no difference. It's the same issue. When do I get a difference? Maybe when one of you joins me. Okay? Now I can be the strongest or the weakest person on the planet. Okay? So when we're looking at large partial charges, we need to look at the difference between atoms in a bond. We have bonds. Do we have a large difference in electronegativity between oxygen and hydrogen? Yes. So oxygen or hydrogen should carry what charge? Positive, because it is lower in electronegativity than oxygen. Everybody remembers our electronegativity trends? Okay. If you don't, definitely talk to me. We need to make sure we got that nailed down. Okay. So hydrogen comes out as an extreme positive. Whoops. Which means the oxygen comes out as an extreme negative. What happens to the other hydrogen? Extreme positive. To have a partial charge, I've got partial charges here, but we're referring to the molecule now, not the bond. Do I have a charge on either end of my molecule? I've got two positives. Okay? They're going to be equally poling, and if they equal pull, it's nonpolar. What else do we have to evaluate? It's not just Lewis structure, it's our Vesper or our shape. Okay, so we have to layer our information in. And really, when we look at water, we should be referring to it as the bent shape. In theory, this is mostly review. Okay. There are a few people that went through the 130, well, even 230 should hopefully have gotten through Lewis structure. So everybody should be okay relatively there. So with that bent shape, now what happens? Whoops. And a negative on the other. We get a net pull towards the oxygen. We have this large partial charge. Okay? Small size. Why is small size going to be relatively important? No, that's going to be referencing back in the bonds there. Okay, let's think about what we need to live every day, constantly, right now. What do you need? Your oxygen. Okay. Let's say oxygen was massive. Okay. We need however many millions of oxygen molecules per second. Oxygen is massive. Okay. Imagine a beach ball size oxygen. You now have to ingest that beach ball size oxygen and expel its partners. What are the odds that a large molecule is going to interact very well with everything? No. So the smaller size of the molecule also contributes to its importance. Multiple symmetries. Why is symmetry going to be important? What's that? It's going to be how it connects to other molecules. Water, because of all those different symmetries, in one orientation can make the same types of connections. Okay? If we picked a different molecule like ethanol, not quite as symmetric, one orientation limits some of the interactions. But because we have lots of symmetries with water, we get all of those interactions all the way around relatively quickly and easily. So symmetry becomes very important. Okay? And then we run into the next two bottom parts, hydrogen bond donor and hydrogen bond acceptor, okay, which gets into your statement about kind of bond strength. Okay? That large partial charge means that that charge needs to get neutralized. Everything's striving for neutrality. If we had methane, okay, methane is neutral, no charge. Does methane want to interact with anything? Okay. There's not really any driving force for it to interact with anything, which is why when we look at methane in its natural state, it is a gas, not a liquid or a solid. Okay. Why is having those large charges help us out? They'll want to react. Do we want atoms to react with each other to make us? If none of our atoms interacted, what happens? We don't live. We don't exist. So we need this kind of strong cohesive force to help keep our molecules interacting with each other. So our hydrogen bond donor and our hydrogen bond acceptor, what are those referencing? As a hydrogen bond donor, what is it contributing? A large partial positive. What is our large partial positive in this case? The hydrogen. A hydrogen bond acceptor. Well, if the other one's a positive, the other one needs to be a negative, and our hydrogen bond acceptor ends up being the oxygen. Okay? So it's how those things interact in a larger, broader sense. But not everything is water. We have a bunch of other molecules out there. We even have structures similar to methane in our bodies. They must also interact with water. Well, why must they interact with water? What is the percent water in our body? 70, 80%. Okay? So everything in our body has to interact with water in some fashion. And it can be a negative interaction. It can be repulsed from it. That is going to contribute to structure and shape. Okay? What this really brings in, and I'm kind of a big fan of this, is looking at intra and intermolecular forces. Everything in biochemistry boils down to bonds and forces. Really, all chemistry in general boils down to these two things. Okay? So we need to be able to look at a structure. Okay? And when we look at a structure, what are we going to see? Are we going to see bonds or forces? Bonds. Okay? Inter or intra is our bonds. So if I just have a structure of water, really all I can see are the bonds, because that's within a single molecule. If I want to look at intermolecular, what do I have to do? I need a second molecule. That second molecule is now going to give me the option for forces. Really what we're looking at is taking any two atoms, and I just want to see how they interact. What happens if they interact really, really, really strongly? What do I call it? Begins with B. A bond. What if they don't interact quite as strongly? Not necessarily repulsion, just forces. Okay. Do we have differences between bonds and forces? Yeah. Okay. Do we have differences within bonds? Yeah. We have three primary types. Non-polar covalent, which I'm lazy and call covalent, polar covalent, and ionic. Okay. Those different bond types then affect their molecular shape. If I bring in another molecule with different bond types, that's going to affect its molecular shape. And I bring those two things near each other, I'm now looking at how those bonds affect each other in a force type situation. So if I have two compounds that are all purely nonpolar covalent, what is the only type of interaction they can do? London dispersion. That's it. Hence the color wheel. If we have a polar covalent molecule, what forces am I going to primarily be looking at? Dipole-dipole. Do I also have London dispersion? Yeah, I will always have everything weaker than it. I tend to only focus on the strongest one. Why the strongest one? Two people are running at you. A really strong person and a really skinny person. Which one are you freaking out about? Okay. The strong person. It's going to have the larger effect on your face. Okay? So we tend to keep our focus there. We just have to remember the rest of them are also there. If I have a polar covalent bond that generates a dipole-dipole force, what should I then be thinking about? Do I have hydrogen bonding? Well, how do I know I have hydrogen bonding? I have a hydrogen bonded to fluorine, oxygen, or nitrogen. Why do we have to have the hydrogen bonded to fluorine, oxygen, or nitrogen? We're generating a dipole-dipole force. If the hydrogen is bound to anything other than fluorine, oxygen, or nitrogen, what do we not have? A dipole. If you don't have a dipole-dipole force, you can't have hydrogen bonding. Okay? So you may have remembered or heard that differently, but it's coming back to the origins. Hydrogen bonding is a dipole-dipole force. If you don't have a dipole-dipole force, you don't have hydrogen bonding. Okay? So let's do a real quick test on that, because I know the homework asks about it, and it usually freaks people out. Let's try this. Hydrogen bonding or not?
No,
Why not?
it's in one single molecule.
There's only one molecule, so I can't have hydrogen. That one molecule can't be hydrogen bonding. Okay, so what if I said, could this one molecule potentially have hydrogen bonding? Yeah, okay. Let's try then that. Hydrogen bonding? It's a little bit of a gray area. It might help if we attach something to the other end.
Non-polar covalent.
The bond in the OO is nonpolar covalent, which means London dispersion. Do you have two dipoles? Nope, which means not hydrogen bonding. Okay? Tricky. Let's make one quick change. Do I have hydrogen bonding now? Yes. What type of bond is there between oxygen and carbon? This may get at a larger issue. What type of bond is that? It is a polar covalent bond. If I have a polar covalent bond, I am generating a dipole. What type of bond was there between the OH? A polar covalent bond, whoops, wrong eraser, which then means a dipole. When I look at the interaction between a dipole and a dipole, what kind of force do I have? Dipole-dipole. Now that I have a dipole-dipole force, I need to evaluate, do I have a hydrogen bonded to oxygen, nitrogen, or fluorine? Well, there's my hydrogen. Is it bonded to oxygen, nitrogen, or fluorine? Yes, that is now hydrogen bonding. Okay. Where you might be getting confused is the strength of that hydrogen bonding interaction. It's not what the question asked. Right? We're asking, is it hydrogen bonding? Okay. So let's throw in one more quick change on this. Because you didn't all get that perfect. I don't blame you. Carbon. Hydrogen bonding, or not? So in blue. Is that hydrogen bonding? Why not? I have a dipole, carbon-oxygen.
Carbon-hydrogen.
What type of bond is there between carbon and hydrogen? A nonpolar covalent, which means London dispersion, no dipole. Without a dipole-dipole force, I cannot have hydrogen bonding. Okay? So we're getting, some people seem to be getting that right off, some people maybe not. do we need clarification on how you can quickly identify nonpolar covalent, polar covalent, ionic? Should I just say it anyway? Okay. Nonpolar covalent. What's our rule? How do we know we have a nonpolar covalent bond? And officially, it's only a rule of thumb. The absolute rule, difference in electronegativity. How many people want to memorize the electronegativities? Yeah, so we need a rule of thumb. Same to same. So carbon to hydrogen, oxygen to oxygen, hydrogen to hydrogen, fluorine to fluorine. That's same to same. Okay? Is carbon the same as hydrogen? No, so our rule isn't complete. What other classifications are nonpolar covalent? Carbon to hydrogen, okay, is defined as nonpolar covalent. Okay. I'm going to skip for the moment polar covalent because that one, believe it or not, I think is the easiest and hardest of all of them. How do we know we have an ionic bond?
Metal plus carbon.
Metal and non-metal, as far as biochem goes, that works. The other thing you could look for is ions. Like, do you see a positive or negative? You have an ionic bond, okay, or an ionic interaction. Okay. Sometimes you won't see the ions because they'll hide it, they'll bury it behind a metal. Okay. So you do have to watch out for that. The metal, non-metal is probably a little bit better of a definition. Okay. Which now takes us to what I said was the easiest one and the hardest all at the same time. Polar covalent. What is a polar covalent bond? And you never had me as an instructor. Everything else. Okay? So you have to memorize ionic, you have to memorize nonpolar covalent. Anything that doesn't match those definitions is by definition polar covalent. Okay? You then pair those bond types to their corresponding forces across the way. That sets you up with your baseline. You can then change different molecules, bring in different parts, and see how those different parts interact. Kind of make sense? Okay. Why is this important to us? Okay. Phase transitions. Okay. Which has the higher melting point? CO2 or H2O? Why does H2O have a higher melting point? Because of, and so this is where we have to be careful, hydrogen bonding. Which of those two molecules has the stronger bond? CO2. We tend to say, well, that can't make sense, and that's one of the reasons why people get confused with bonds and forces and strength of the bonds, because they reference melting points and boiling points. What is breaking when we melt or boil a substance? When I boil water, it turns into oxygen and hydrogen? No, it turns into water vapor. It's the forces between those individual molecules. The forces are over here. We don't touch the bonds when we do phase transitions. Okay? So we have to be careful when we're thinking about our primary properties that when we think about when we look at a molecule. Most of those properties are associated not with the bonds, but with the forces that the bonds generated. Okay? Which is a tricky subject to nail down. Okay? So be very careful when referencing bonds, which I know is irritating because one of our forces happens to be called hydrogen bonding. Probably the worst job of nomenclature in the history of science. So let's blame the biologists. That's probably not true. It's probably a chemist. Okay? So our phase transitions come out of our forces. How about solubility? When I mix water with oil, am I changing the bonds when I mix those? No. I'm looking at how the forces interact. Okay? So when I think about solubility, water and oil, do they mix? Why not? It's the forces. Water has hydrogen bonding. Oil is just carbons and hydrogens. Carbons and hydrogens are nonpolar covalent bonds which generate London dispersion forces. When I have two things dissolve, I have the like dissolves like what dissolves like what? Begins with F. Forces. Okay. Hydrogen bonding is similar to London dispersion. Is that true? No. Which means they don't mix. That's where it's coming from. Okay. What about reactivity? Okay. How can we predict reactivity? How do we know we have a strong acid? That guy is always excited every semester. And you laugh now, but wait for an exam. Name an acid. What's going on with hydrochloric acid? We have a polar covalent bond, which means we have a dipole or hydrogen bonding potential there. What happens to the strength of that bond then if we have a stronger force? Gets weaker, and we have the potential to break that bond apart. By looking at that dipole, we can start to reference something about the bond characteristics. If we know something about the bond characteristics, we then know potentially how that bond can change. Right? Our Bronsted-Lowry acid bases, Lewis acid base, electrophiles, and nucleophiles, those three definitions should have been hammered into you, even if you went through the quick and dirty versions of chemistry. Okay? When we start actually directly referencing those, if you need any help, just let me know, and we'll go through those definitions again. Okay?
Can you repeat, not the definitions, but why is it if this is stronger force, it will break them? I'm confused. If it's a stronger acid, do you get what I'm asking?
If this force becomes stronger, what does that do to that bond? It starts to pull it off. So it can dissociate quicker. If it dissociates, what do we end up with? H+. What's the definition of Bronsted-Lowry acid? Hydrogen donor. There's our H+. Okay? So we can use our bonds and forces to help us predict reactivity. Okay? We do need to watch out for some traps. We need to know the bond type, we need to know the force type, but then we also have to worry about molecular shape, okay, which gets into VSEPR models. Biochemistry, this is a relatively minor topic, but I wanted to at least address it. Why is it a minor topic for biochem? Polar or nonpolar? I hate polar and nonpolar, so let's go with nonpolar covalent or polar covalent bond. Polar covalent, which would suggest what force? Dipole, dipole. What if I double that bond? Actually, is this a valid Lewis structure? This is a weird term. Yes, it is a valid Lewis structure. It doesn't invalidate anything to do with Lewis. What does it invalidate? VSEPR. And VSEPR, we want our electrons to align as far away from each other as possible, so we get the linear shape. We said the carbon-oxygen double bond was polar, which should generate a dipole. If I draw in another carbon-oxygen double bond, I also have another polar bond, but according to VSEPR, they're on opposite sides. Now I have a nonpolar molecule, even though I have polar bonds. Okay? So we have to evaluate the molecular shape as well, and that's where we need to go into VSEPR. Why does this become relatively a minor topic as far as biochemistry is concerned? Remember that image that we started off the whole lecture with, the ATP synthase? Okay, we saw those little blobs. Anybody know what a little blob represented? Tiny, just one of the little tiny little blobs? An atom. How many atoms were in that? A lot. How symmetric are we going to get each of those bonds to be? Not very. So this whole issue with VSEPR and molecular shape really only applies to tiny molecules, plays a much larger or smaller role when we move into biochemistry looking at proteins and larger things, because we don't get that symmetry to cancel out those polarities. Okay? So we do need to at least keep in mind that we have to look at the whole molecule, but it's relatively minor. Okay? VSEPR review, we've got our different shapes. Okay? So you can find textbooks has different things on this. I prefer this kind of summary. So you would look at your Lewis structure. You'd say how many groups of electrons. You'd classify its electron geometry. Then look at bonding versus non-bonding. Come up with the molecular shape. We good? Ish? Okay. That also brings in bond angles. I think I might include that just because Sapling asked a question about it. Okay. Relatively minor review stuff. What can we do with these interactions? So why does salt dissolve in water and oil not? What is salt? And oil, for the sake of brevity. Why does salt dissolve in water but not our oil? What is our force for water? Strongest potential force. What is our strongest potential force for our oil? Or oily? Why not? London dispersion forces. What is our strongest potential force for sodium chloride? Ionic. If we applied our like dissolves like rule, hydrogen bonding in comparison to London dispersion, different or similar? Different. Should they mix? No. Hydrogen bonding versus ionic, different or similar? Ooh, different. They're more similar than London dispersion, okay, but they are different. Why is salt dissolving then if they're both different?
The difference in charges. Electronic difference.
This one gets a bit odd because what we're thinking about is what are those forces? So hydrogen was our positive, so that needs to be connected to which atom? Chlorine. Okay, our chloride with our negative, and we're looking at that interaction. Okay. For it to dissolve, that interaction to the chloride needs to be stronger than what? It needs to be stronger than that interaction. Okay. Is this hydrogen bonding ionic force, keyword there, force, stronger than the sodium chloride bond? No. Why does it dissolve? Pen, thank you. How about these two forces? Are they stronger than that one force? Or how about, oops, that should be blue. These three forces. When we look at the salt dissolves, it's not a single ion hydrogen bonding interaction, it's multiple. Those sum total of interactions are what contribute to the solubility of our ionic compounds. Do we get a similar interaction when we look at London dispersion? No, there's no charge there. There's no charge associated with the LDF. There's no reason for hydrogen bonding to interact with any of our oil molecules. So we can do kind of an oil comparison. Or not oil, force comparison. Which is kind of neat. At least I think that's neat. Okay? So we're looking at kind of a larger picture. Okay? It's not always as simple as force and force. I'm on time.
Oh, nice.
So far. It's okay. It does that when you're tired. How does soap help oil dissolve? What is soap? Well, it's an S, it's an O, it's an A, and a P, right? Okay, well that's not very useful anymore. We need some kind of structure. What's our structure of soap? Nobody did a lab on that, really? I shouldn't talk. I didn't make anybody do a lab on it either. 1, 2, 3, 4, 5, 6. There's soap. Okay. All of the lines representing bonds between carbons. Carbon's supposed to have 4 bonds. I only see 2 bonds there. Hydrogens, okay, so each of those lines representing a sequence of carbons and hydrogens. Okay. What type of force would we expect from carbons and hydrogens? A London dispersion force. What was the force that we got from our oil? Is London dispersion similar to London dispersion? Okay, so that's a similar interaction. Whoops, drew that, of course, backwards. What's the strongest force in hydrogen? Water. We had hydrogen bonding. What's our strongest force at the other end of that molecule? There's our big hint. We have ionic, we see that ion. What can happen? I can get a hydrogen ionic interaction, and I can get multiple water interactions with that end, which overcomes our ionic interaction on its own, which means that half of the molecule is soluble in water. What about the other half? Not soluble in water. What was the question? Soluble in oil. So how does soap help oil dissolve? It surrounds it. It takes all of the nonpolar part of the soap molecule and it buries itself in the oil. It then completely surrounds it, which now means on the outside of it, what do we have? Just the polar ionic part that does interact with water. And what we end up forming are things known as micelles. Why are micelles particularly important? What happens if we scale up that micelle? Okay, we can get a liposome. If we scale up a liposome even further, what do we end up with? A bilayer sheet, also known as cells. Okay, that is the barrier between our cells and the rest of the environment. It's all coming from soap. So why is soap a particularly dangerous thing for bacteria and why we wash our hands? What is the soap doing? Breaking down our bilayer sheets. If the bilayer sheet falls apart, do we have a cell anymore? No. Okay, and it tends to destroy it. Okay? When we're referencing the bilayer sheets, why do we call it bilayer sheets and not, say, a liposome? What is the difference between a liposome and a bilayer sheet? Because cells are just flat things, right? One side of it is the outside of the cell. The inside of it is the inside of the cell. And it's just a flat thing, right? No, it's not flat. What is it? Spherical. Why are we calling bilayer sheet flat? Scale of size. Okay. The Earth is what? Round or flat? That hopefully is not a debate. Okay. Is round, and yet when we walk outside, we don't feel like we're constantly falling around the Earth because at that scale, it's flat. Okay. That's the same idea with our imaging here. Just to bring in some flat Earth stuff. Why not? Water is awesome yet again. Water can decompose into 2 species, H plus and OH minus. What is special about H plus? Acid. Good answer. What is special about OH minus? Base. So water can dissociate into our acids and bases, which are responsible for a lot of our primary reactivities. Right? So acid is something that increases the H plus. Because we're in water, if the H plus goes up, and this is in equilibrium, what must necessarily happen? This goes back to the 152 people to help me out. If H plus goes up, could actually go to everybody because the answer's on the slide. The H2O increases. How does it increase? I need an O and an H to make H2O increase. What happens to the OH minus? It must decrease. Okay. So when we're looking at our acids and bases, it's the balance of our H plus and OH minus. Will, yes, change the amount of water present, but more importantly, it's going to change the amount of H plus relative to the OH minus. Why do we not typically look at the water change? 70-80% of our body was what? Water. If I change the H plus concentration by 50,000, does that have an effect on the water concentration? No. Water is in such a massive concentration that for really all intents and purposes, it's constant, even when we fluctuate the acid and base. Okay? So we tend to not worry about the water as much. I think I've seen some nasty MCAT questions that push at water concentration. It's not nice, but it does happen. You have to really get into equilibrium and all sorts of other fun stuff like that, which I'm going to say is your 152 class and hopefully not have to talk about it, because I don't really want to do it, if I'm going to be honest. Okay? Why does this become relevant for us? Well, didn't we just talk about solubility? Well, what molecule do we have here? Rhymes with oic acid. Benzoic acid. When we look at this part of the compound, I couldn't come up with anything faster than that. This part of the molecule, what kind of forces would we expect? London dispersion. We just have carbons and hydrogens. At the other end of the molecule, what do we have? Hydrogen bonding. Would we expect this molecule to be soluble or insoluble in water? Soluble on one side. Okay, that's not a bad answer. There's a bit of an issue with the way this is drawn. Okay, are all those bond lengths or sizes shown the same? Not really, actually. That benzene ring is shown a little bit smaller. It's significantly larger, which then means the overall contribution of this molecule's intermolecular forces is what? London dispersion, which then means not particularly soluble in water, or limited solubility. Okay? How could I make it more soluble? Okay? This hydrogen bonding interaction may be similar with water, but I can really only get one. How could I increase the possible interactions with water? It rhymes with bionic was a bad choice, but that's all I got. Bionic. What if we made this ionic? Well, if it's an ion, that is now so charged that it needs to neutralize as quickly as possible. I can collect a lot more water molecules around it. So how do I make that compound ionic?
Kick the hydrogen off.
I can remove the hydrogen. And I would end up with O minus, and then H plus floating around. Okay? Well, if I took off an H plus, what did that species act as?
Acid.
An acid. Okay? So to get that hydrogen off, what did I need to add? A base to remove that acidic hydrogen. I now have that ionic interaction, which then means a lot more water molecules flock to this thing, which then means more soluble in water. If we have an ionic spot, our compound becomes much, much, much more soluble. Okay, which is very important for biochemistry because we've got very large molecules, okay, with lots of polar covalent bonds that aren't really contributing, and nonpolar covalent bonds that might be contributing to the lack of solubility. And yet everything stays soluble largely because of ionic sites within those molecules. Okay? Why is this again important for us, particularly with relevance to the last thing? What happened if I put the hydrogen back on? It's insoluble in water. So if I'm looking at my cells that have lots of negative charges and positive charges floating around in them, and I now change the pH, I'm adding hydrogens. Those hydrogens will seek out what in my cells? What are the hydrogens going to seek out? Negative charges. Those negative charges are now no longer negatively charged, which means how well do they interact with water? They don't. So all of a sudden, my system, at a lower pH, I start seeing things precipitate out of solution. They lose their solubility. Well, if all of a sudden my blood became solid, I'm just chilling, that's a bit of a problem. Okay? What if I did the opposite? I added a bunch of hydroxide. What are those negative charges going to seek out? The hydrogens, changing the charge of the structure again. If the charge changes of the structure, what happens to its solubility? Also changes, and I could potentially also see things precipitate out of my blood. That's a problem. Okay? So when we're talking about acids and bases, it is of critical importance because a subtle change in the pH can change the solubility drastically. That drastic change in pH, or that drastic change in solubility, can be the difference between life and death. Okay? So, this is going to get ugly, but we got to deal with it. So, and this is primarily for anybody that didn't have 152. Okay? And if you had 152, maybe this will help a little bit. What we're going to start talking about is equilibrium. Our reactions can go forward and backwards. Okay, so that's what we're starting up at the top. We have A going to B. Okay? The rate of that reaction, going from A to B, we'll define as that rate constant sub K, or the lowercase k f. So the rate constant for the forward reaction. Okay? That forward reaction produces a new species. Well, what can that new species do? It can react. It could react in such a way that what does it make? A. So it just went backwards. Okay? That new reaction is going to have a new rate constant associated with it, or a new term representing its rate. That gives me K sub R. Okay? I can then compare and do all the solves, activation energies, and all that fun stuff, and figure out what those rate constants are. Okay? And when we think about chemistry, we're typically focused on just driving forwards. Okay? Because in chemistry, I'm trying to make something. In biochemistry or biology, what am I trying to do? Is biology always trying to make something? Okay, are we constantly replicating? May seem like it, but no. Okay? What are we doing in biology? We are maintaining. We are staying the same. Okay? But what is constantly happening in our life? As we exhale, what are we doing? Combusting. We're being broken down. So as we're getting broken down, what must we also do? Build back up. We have to counteract those things. They have to be in constant alignment. They must be in equilibrium. The rate of my forward reaction must equal the rate of my reverse. Okay? Because if they don't, I either go into making more of me or losing me. Okay? Both thoughts potentially scary depending on your point of view. Right? What we then do with that is say, okay, well, if I've got those, I said Kf was a constant, and Kr was a constant. The brackets are referencing the concentration. Okay, so for the forward reaction to occur, what does it need to have? It has to have a reactant. It can't progress forward if there's no reactant. Okay, so I will see the concentrations of my reactants being tied to those individual rate constants. Okay? And just like we would do in any kind of mathematics class, what we will do is group like terms. I will group all the rate constants on one side of the equation, and I will group all of the concentrations on the other side of the equation. And what do I end up with? I have the rate of the forward constant, or a rate constant for our forward, divided by the rate constant for our reverse, equal to the concentration of B over the concentration of A. What is a constant divided by a constant? A constant. It is not 1, because I haven't defined what that constant is. Okay? So it's just a new constant. Okay, well, if I have a new constant, irritatingly, what do? I name it as a new constant. And what name did we come up with? Capital K. Not lowercase k. Capital K. Okay? And that capital K is now known as the equilibrium constant, because it came from saying that those rates were equal to each other, or at equality. Okay? What can I now do with that equilibrium constant? That's when things snowball into a hellstorm, and we'll sort of go into it and then kind of back away from it. Okay? We're really looking at how do we define that, okay? And it's really the ratio of the products and reactants after the reaction has achieved that point. Okay? I can never look at the equilibrium for a reaction that is going in one direction. Because the whole point of equilibrium is saying it comes back. Okay? So I have to be at equilibrium. So, well, if we think about biochemistry, where are we constantly? At equilibrium. And every so often, we'll get pushed out of equilibrium, and our body will always try and achieve that, or re-achieve that. Okay? And it'll do it a variety of ways. How do we push out of equilibrium? Hold your breath. See what happens. Okay? Eventually, your body freaks out, and you inhale. Okay? Or exhale, whichever way you do it. Okay? So we do have these stresses, and they're happening to our everyday life. And those stresses affect our reactions, but we're constantly trying to move back to that state, okay, to that equilibrium constant. Okay? So, how do we apply this to our acids and bases? Well, if I look at an acid and I react it with water, what do acids do? They donate protons. Well, the proton is just the H, right? So if that gets rid of a proton, it becomes A minus. What did it get rid of the proton to? Water, and that becomes H3O plus. Okay? Once I've allowed that reaction to do its thing and achieve its balance of forward and reverse, I then have an equilibrium, and I can now look at the equilibrium constant for that expression. I can do the same thing for a base, except what does a base do? Accepts a proton. Okay? Where did the base get the proton from? Water. So we take the hydrogen away from water, give it to the base, and we have Hb plus and OH minus. Once I let the base do its thing, it achieves equilibrium, and I can now reference its equilibrium constant. Okay? Whoops, whoa. Okay, so that did not show up the way I wanted it to. So our equilibrium expressions for these, for our acid, we would get KH3O plus times A minus over what? Because it's products over reactants. What are our products? Sorry, reactants. HA and H2O. That is our equilibrium expression. For those of you that went through 152, you should be screaming internally. You don't count H2O. It's a pure liquid. Why? Why do I not count it? Okay, it's a pure liquid. Why is that relevant? We actually already gave the answer out. It's not an equilibrium thing. Water is our solvent. It's there in vast concentrations. I can change the concentration of my acid, which will change these species. Okay? And it does have an effect on the water concentration. But if water is 70 to 80% of my solution, how much of its concentration changes? Little, which then means H2O is a constant. What was K? A constant. What do we do with similar terms? We group them. So we take the concentration of H2O, we multiply it by our K, and we'd end up with a new expression. That new expression would be our H3O plus, and I'm definitely out of time. Next class is like yelling at me internally. I can see it. I can feel their beady little eyes. We'd end up with this new expression. Okay? Can I say it's K, though? Why not? I multiplied it by the water. So I can't call it just K. What should I call it? YKA. Because it came from the acid. Okay? You should be able to do the same thing with the base. We'll pick up there tomorrow, though I won't solve through for the KB, but we do the same ultimate idea. It's then going to be what can we do with these terms and manipulations, which is